All right, welcome to Math TV with Professor V, areas between curves. Now, we've studied before how we can use calculus, particularly integration, to find the area underneath a curve. Now we're going to see how we can also find the area that is enclosed between two curves. So here we're going to look at this first case or scenario where you have two functions. We're going to call them f of x and g of x. And say we're interested in finding the area between these two curves on the interval from a to b, which is precisely where they happen to intersect as well. Okay, well, remember when we started the process of finding the area underneath the curve, we first estimated the area by using rectangles. And the thought process with how we find area between curves is very similar. So imagine if we were to take a bunch of rectangles and approximate the area underneath the curve. Well, the base of each of these rectangles, we would still use delta x or dx to represent. And then now the height of the rectangles could be found by taking f of x and subtracting g of x, right? So that is basically where we get our formula from to find the area between two curves. So your limits of integration a to b is going to match where they intersect. And then the function that's on the top always goes first minus the function that's on the bottom. That way you get the height of the rectangle, and areas between curves will never be negative because it's area enclosed by the two curves. Okay, and this is when we're integrating with respect to x. Now, what if f of x is not always the function that's on the top or greater than g of x? What if you have another situation illustrated below where maybe f of x and g of x intersect multiple times? For some portions, g of x will be on top, and for other portions, f of x is on top. Well, what do? You're going to have to split up your integral. That way, remember, the area between curves is always going to come out to be positive. So the idea is you're going to integrate from a to b. Those are going to be your limits of integration from the very beginning to the very end. And the area between these curves is given by the absolute value of f of x minus g of x dx. So let's see how we would just set this up hypothetically. We would need to have three separate integrals. The first one would go from a to c. And then on that interval, notice how the function in blue, f of x, is on top and g of x is the function that's on the bottom. So to get the height for each of the rectangles, we would have f of x minus g of x on that interval. Then I would pick up right where I left off. So since I left off at c, that's where I would start, and then I'd go up to d. And then now notice on this interval here, g of x is the function that's on the top, and f of x is now the function that's on the bottom. So then I would have g of x minus f of x dx plus, and then my last integral would pick up right where I left off again. So I would go from d to b, and then now f of x is on top again, minus g of x dx. Okay, so that's basically how you would set it up if there wasn't one function that was always above another one. Now, what if instead you have functions of y? Well, you would set it up very similarly. It's just now you would stack your rectangles in the y direction. So it would make more sense in this case to make rectangles this way, right? To approximate the area underneath the curve. And you would actually integrate with respect to y, because the base of each of these rectangles would be a delta y or dy when we're integrating. And then the height here of the rectangle, remember, it's not going to be negative. So you always have the larger function minus the smaller function. In this case, it's going to be right minus left. So your limits of integration, everything has to match. Your limits of integration are going to be in terms of y. So you're going to start from c up to d. You would have f of y, since that's the function that's on the right, that one's larger, minus g of y dy. So this is right minus left, okay? And if you get a negative value, then you know you did something wrong, okay? Because area between curves is always going to be positive. Okay, So let's look at some examples. There's going to be graphing required for basically any problem that you do here. So make sure you do your graphs nice, neat, and labeled. Example 1. So sketch the region, draw a typical rectangle. I will explain what that is, label its height and width, and then find the area of the region. So we have y equals sine x, y equals e to the x, and they're specifically already telling us that they only want the area between the curves on the interval from 0, x equals 0 to x equals 2. Okay, so let's just set up a little table before we graph. So I have an idea of what everything's going to look like. I mean, I know what e to the x and sine x look like. You should. But let's make a very nice specific graph. So we're only interested in plotting values for x between 0 and pi halves. So let's just do 0. Pi over 4 sounds like a nice halfway point, and pi halves. That should be enough because we know what e to the x looks like. E to the 0 is 1. Then you can use your calculator here. Just take e, raise it to the pi over 4 power. You get about 2.2. And then e raised to the pi halves would get you about 4.8. And then sine here, you should know what it is. So sine of 0 is 0. Sine of pi over 4 is rad 2 over 2. So that's 0.7 approximately. And sine of pi over 2 is 1. Okay, so I don't need to label my y-axis any more than maybe 5, right? Since e to the pi halves is 4.8. And the x-axis, I'm only going to label up to pi halves. So here's our y-axis. Here's our x-axis, 1, 2, 3, 4, 5. And then I'm only going to label up to pi halves. Say that's here. And so this would be pi over 4. Okay. So let's start off. Let's graph e to the x. And I will graph it in light blue. So when x is 0, e to the x is 1. At pi over 4, it's 2.2. So 2 and a wee bit more. And then at pi over 2, it's equal to 4.8. Okay, so here's e to the x, just a little sliver of it. And then sine x, I'll graph that in purple. So at 0, sine of x is 0. At pi over 4, it's 0.7, so it's just crawling up. And at pi over 2, it's 1. So it's really stretched out, right? And we know that's the largest value sine of x is going to take on. And that looks good. Make sure you draw it nice so it looks concave down, right? Okay, so now I'm only interested in finding the area between the curves from 0 to pi halves. So let's just fill in specifically what that is. So that's this shaded region right in here. That's what I want to find the area of. Okay, so this was y equals e to the x. And this was y equals sine x. Now the problem asks us to draw a typical rectangle and label its height and width. So it would make sense if we were to set up this integral that we would stack our rectangles in the x direction, right? So this is a typical rectangle. You just draw a rectangle somewhere between the two curves to demonstrate how you would begin the process of computing the area between them. Now, what would its height be? Well, the height would be the top function minus the bottom function. In this case, that would be e to the x minus sine x, which is why our graph was helpful. And then the width, or the base, in this case is delta x. And this is basically all the prep work. That way now you can just set up your integral and be done with things. So this means now the area between the curves is going to be given by the integral from 0 to pi halves. The height, I have it right there. It's e to the x minus sine x. And the width is dx. Okay, now we just antidifferentiate. So antiderivative of e to the x is e to the x. Antiderivative of negative sine x is going to be positive cosine x. And then I'm going to evaluate this from 0 to pi halves. So now we're going to have e to the pi halves plus cosine of pi over 2 minus e to the 0 plus cosine of 0. Okay, so e to the pi over 2, I'm just going to leave it. That's e to the pi over 2. Cosine of pi over 2, that's 0, so that's gone. And then minus, now e to the 0, that's 1, and cosine of 0 is also 1. So I'm left with e to the pi over 2 minus 2. All right, and that's our answer. Just leave it alone, exact form like that. two irrational numbers together, e and pi. Check that out. Okay, good. Now let's move on. A lot of the time, you won't be given the interval. It won't tell you, oh, from 0 to pi halves. You're going to have to find that yourself. So we're going to look at what to do. So example 2, we want to find the area between the curves y equals x squared and y equals 4x minus x squared. Now, think about it. X squared, that's a parabola that's opening upwards. And then 4x minus x squared, that's a parabola that's opening downwards, right? And it's been shifted over to the right. So to begin, we need to find where they intersect. So first, let's find the points of intersection. Okay, so I'm going to set the functions equal to each other. So I'm going to set x squared equal to 4x minus x squared. And then I'm going to set this whole equation to 0. So 2x squared minus 4x would be 0. Factoring out the greatest common factor, I have 2x times x minus 2 is 0. So they intersect when x is 0 and x is 2. So now I know I'm going to make my table of values, and I'm just going to list in values for x, starting at 0, ending at 2. So I'll have a column for x, one for x squared, and then one for 4x minus x squared. Let's see, we only need to go from 0 to 2, so why don't we just do 0, 1, and 2. How does that sound? Okay, so x squared, that's easy, 0, 1, 4. And then 4x minus x squared, that's going to be 0. 4 minus 1 is 3. And then that's going to be 8 minus 4, so 4. So let's see, looks like on the y-axis, I'm only going to have to go up to 4, right? And on the x-axis, we're only plotting between 0 and 2. So again, we're just going to stay exclusively in quadrant 1. X-axis, y-axis. So say that's 2, this is 1, and then we'll go up to 4. 1, 2, 3, 4. Okay, so 0, 0, let's start with x squared. 1, 1, 2, 4. So this is y equals x squared. Now y equals 4x minus x squared, also 0, 0. Then it will go through 1, 3. Ooh. And then lastly, 2, 4, where they intersect, and we expected that. Okay. So this is y equals 4x minus x squared. So let's shade the area that we're trying to find. It's all of this. And then now let's draw a typical rectangle. So it makes sense to stack the rectangles, or to build them in the x direction, right? Since we always have one function on top, one function below, and they're both functions of x. So it looks like it's the easiest way to set things up. So here's my typical rectangle. And then now I need to give its height and width. Okay, so what's the height of this rectangle? Well, which function is on top? It's 4x minus x squared minus x squared is the function on the bottom. And then let's clean things up and combine like terms while we're at it. So this is 4x minus 2x squared. Nice. And then the width is equal to delta x. So now we're ready to set up our integral. The area between the curves is going to be given by the integral from 0 to 2 of 4x minus 2x squared dx. And then now we can go ahead and anti-differentiate. Antiderivative of 4x, that's 2x squared. Then we'll have negative 2/3 x cubed from 0 to 2. And so this is going to give me 2 times 2 squared, so that's 8 minus 2/3 times 8, that's 16/3 minus, and then 0 for both those lower limits. Don't get lazy just because the lower limit's 0 and automatically assume when you plug it in to your antiderivative you'll get 0, because every now and then, you know, you'll have like a e or a cosine and you'll get something that's not equal to 0 and it'll sneak up on you. Okay, and then what does this give us? So 8 is 24 over 3 minus 16 over 3, that's 8 over 3. Beautiful. Normally, when you do area between curves, the integrals themselves will not be too hard to compute. You're really, the meat of the work is going to be in the setup, in the graphs and all of that. Okay, are you having fun? Let's look at another example. So this time we have 4x plus y squared equals 12 and x equals y. Now let's see here. Do you know what 4x plus y squared equals 12 looks like? It's a parabola, right? Since only one of the variables is squared, but it's opening up horizontally. Actually, it's going to open up in the negative x direction. And then I have x equals y. Well, that's a line, right? Normally we see it as y equals x. So maybe they're giving us a little bit of a hint, right? And get x equals y instead. We'll see. Let's first find the points of intersection. Now, it's really just as easy to find the points of intersection in terms of x or y, but I think this time we can just do it in terms of x, and then it might be easier for us to build a table, okay? But sometimes you might need to do it in terms of y, and it's not that big of a deal. So since x equals y, I'm just going to substitute in x for y into the first equation. So I'm going to have 4x plus x squared equals 12. So then we have x squared plus 4x minus 12 is 0. And then I can factor this. So this is x plus 6, x minus 2 is 0. So x is equal to negative 6 or 2. So these are the two x values where the curves intersect. So now I'm going to make my table. Notice this parabola here, though, it is not a function of x. So what I'm going to need to do is isolate y, right? And y would be equal to plus or minus the square root of 12 minus 4x. So I'm going to use that when I'm making my table now. So we'll have x equals y, that one's easy, and then y equals plus or minus the square root of 12 minus 4x. Okay. So here we go. Between negative 6 and 2, we have quite a few x values, so maybe we'll just take them 2 units apart. Okay. So I'll go, meaning I'll do negative 6, negative 4, negative 2, 0, and 2. And that should be enough. If it's not, then just add to your table, okay? But we'll just see from here, especially since I know one's a parabola, one's a line, this should be sufficient. And then let's fill in the table now. So x equals y, I don't even have to think, I'm just gonna copy everything over. And then y equals plus or minus rad 12 minus 4x. So this would be plus or minus rad 36, right? If I plug in negative 6 for x. So then this is going to give me plus or minus 6. All right, substituting in negative 4 for x, that's going to give me 12 plus 16 under the radical. So I'll have plus or minus square root of 28, which is about plus or minus 5.3. And then if I plug in negative 2, that's going to be plus or minus rad 20. So that's about plus or minus 4.5. 0, I'm going to get plus or minus rad 12, which is about plus or minus 3.5. And then if I plug in 2, I get plus or minus square root of 4, which is not approximately, but exactly equal to plus or minus 2. All right, so let's see. The largest and smallest values of y that I got were 6 and negative 6, respectively. So I'm going to have a lot of stuff going on the y-axis. I have to go up to 6, down to negative 6, and then x's are going to be between negative 6 and 2. I'm going to go a little bit past that because I know the vertex of my parabola is going to be a little further in the positive x direction. So let's just make a nice even square. Sound good? Okay, this looks nice. This is the y-axis. Get in the habit of always labeling your axes because before you know it, they're not going to be always x and y. Okay. Here's x. So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Looks good. 1, 2, 3, 4, 5, 6. Beautiful. Okay, so y equals x, that one's easy to graph. It's just a sweet little line. So we have -6, -6, -4, -4, -2, -2, 2, 2 is the last point where they're going to intersect. I mean, I could keep going. Okay. Okay. Clearly my scaling was not perfect, so we'll just do this and it looks perfect now. Great. Okay, this is y equals x. All right, now I need the parabola. So at -6, I have plus or minus 6. When x is -4, I have plus or minus 5.3. So 1, 2, 3, 4, 5, and a smidge more. 1, 2, 3, 4, 5, and a little more. At -2, we have plus or minus 4.5. 1, 2, 3, 4 and a half. And then up. 1, 2, 3, 4 and a half. 0, we have plus or minus 3 and a half. 1, 2, 3 and a half. And then at 2, we have plus or minus 2. And the vertex of this parabola actually sits at 3, 0. Okay. Now let's fill in the shaded area. And see how it would make sense to set up our rectangles and then integrate. Okay, now you tell me, is there always one function that's above the other one? Does it make sense to stack our rectangles in the x direction? Well, you could, but you're gonna have to do two integrals. Do you see why? Because y equals x lies above the graph for this portion here. But then for this sliver over here, it's the parabola that's on the top and the bottom. Okay, so for that reason, it's actually cleaner if instead, I'm gonna undo all this. If instead I build my rectangles in the y direction, right, with base delta y, because now you see we always have one graph that's on the right and one graph that's on the left. In this case, we have the parabola 4x plus y squared equals 12, always on the right. And then the line y equals x is always on the left, okay? Now the thing to remember though, as I said, everything has to match when you set up your integral, meaning the limits of integration have to be in terms of y, then the functions have to be in terms of y, and then you have to have a dy instead of dx. So what I want to do is rewrite the equation for the parabola so that I isolate x in terms of y. So this is going to be 4x plus y squared equals 12. So I'm going to write that as 4x equals 12 minus y squared, which means I have x equals 3 minus 1/4 y squared. Okay, so now let's go ahead and label this rectangle, our typical rectangle. The width in this case is going to be delta y, and the height is right minus left. So the graph that's on the left is the line, and on the right I have 3 minus 1/4 y squared minus y. Okay, so keep in mind for this example, it's easier to integrate in the y direction with respect to y. It's not that you couldn't do it in the x direction, but you'd have to split your integral. And who wants to do that? Okay, so let's set things up. So the area is going to be given by the integral. Now look at the limits. They have to be in terms of y. So you have to figure out where do they intersect in terms of y. And we already have those values. It's -6 and 2. Same values where they integrated with respect to x, or where they intersected with respect to x. So I'm going to have the integral from -6 to 2 I already have the height there. It's 3 minus 1/4 y squared minus y dy. And then if I anti-differentiate, this is going to give me 3y minus 1/12 y cubed minus 1/2 y squared, evaluated from -6 to 2. All right? And then the rest, you could just sit there, plug in, have fun, and you should get 64/3. All right. Looks good. Now let's look at another interesting example with our good friend, y equals absolute value of x. So absolute value of x, that graph has a V shape to it, right? And then y equals x squared minus 2, that's a parabola, shifted 2 units downward. And the x-intercepts are going to be at plus or minus rad 2, 0. And the vertex of this parabola is at 0, -2. Y equals absolute value of x, we know what that looks like. Now, if I want to find where they intersect, you could just think about it. But if you want an algebraic way of doing it, what we're going to do is rewrite absolute value of x piecewise. Okay. So I'm going to rewrite absolute value of x. It's equal to x if x is greater than or equal to 0, and it's equal to the opposite of x if x is less than 0. So say I'm going to find the intersection between absolute value of x and the parabola for the right half of the graph, for x is greater than or equal to 0. So in order to do that, I would set x equal to the parabola, x squared minus 2. So I'll set this equal to 0, so I have x squared minus x minus 2, now plus 2, right? I'm going to move that over. X squared minus x, it should be minus 2, equals 0. So then I'm going to get x minus 2 times x plus 1 is 0. And then they're going to intersect when x is 2 or -1. Now, -1 I'm going to throw away because remember, I used x for absolute value of x because I was choosing values where x was greater than or equal to 0. So I'm only going to -1 is extraneous, basically, for this equation. So x equals 2 is where they intersect. And then I know y equals absolute value of x is symmetric about the y-axis. So by symmetry, it also must intersect at -2. So I know the parabola and y equals absolute value of x intersect at x equals plus or minus 2. Or you could sit there and find the intersection again using -x, but the whole thing's repetitive. Okay, so let's graph. So I basically just need to go plus or minus 2 in the x direction. And I know the parabola has been shifted down 2 units as well. So we need some negative y-axis going on. So here's x, here's y. Let's go down 1, 2, 1, 2, -1, -2. All right. So let's do the parabola first. So we have 0, -2. And then plus or minus rad 2 is where the x-intercepts are, so about 1.4. And then at 2, 2, it's going to intersect with the absolute value graph. So we've got this parabola. Looks so nice. Okay. And then y equals absolute value of x. We know what that looks like, just that V shape. And then they intersect at 2, 2 and -2, 2. So I'll just connect those line segments. Or those lines. I won't draw them as segments. I'll put arrows and they'll keep going. So what's the area that we're trying to find between the curves? It's all of this. And over here. Okay. So let's see, does it make more sense to set up our rectangles, stacking them in the x direction or in the y direction? Well, I would say the x direction because it looks like the absolute value of x is always the function on the top and the parabola is always the one on the bottom. So we could just draw a typical rectangle maybe somewhere here, right? Okay, so the width of the rectangle would be delta x. And the height would be given by absolute value of x minus the parabola, x squared minus 2. Okay? Now notice I'm going to have to split my integral because from negative 2 to 0, absolute value of x is defined to be negative x, and then from 0 to 2, absolute value of x is defined to be positive x. So since the function switches, I'm going to have to split up my integral at 0. So we have the area between the two curves is equal to the integral from negative 2 to 0. We're going to have top minus bottom, so absolute value of x is defined to be negative x minus x squared minus 2 dx plus, then I'm going to pick up right where I left off, 0 to 2, and then now I'll have x, because absolute value of x just equals x over here, minus x squared minus 2. Keep all your lovely parentheses in there. Now notice, though, I mentioned earlier that both of these graphs were symmetric with respect to the y-axis. So why bother doing both these integrals? We can just evaluate one of them and then double what we get because of the symmetry, and that will give us the area between the curves. Which one looks nicer to work with? For sure, the one that has 0 as the lower limit, right, without the negatives. So I can rewrite this as 2 times the integral from 0 to 2 of x minus x squared plus 2 dx. And you want to indicate this is okay to do because of symmetry. All right? And I do require that anytime my students make use of symmetry, they still write out the setup for the original integral. So just check with your teacher how they will require you to show your solution. Okay? And then from here now, I can just start anti-differentiating. So I'm going to have 2 times 1/2 x squared minus 1/3 x cubed plus 2x. I'm going to evaluate that from 0 to 2. And this is going to be 2 times 2 minus 8/3 plus 4 minus, and then I get zeros all around. And so this is going to give me 6/3 minus 8 plus 12/3. So I'll have 20 over 3 after I double it. Okay? Very nice. Last one. Example 5. So use calculus to find the area of the triangle with vertices 0, 5, 2, -2, and 5, 1. Okay, so let's draw this triangle first and then decide our plan of attack. In the y direction, I'm going to have to go up to 5, and in the x direction as well. But I don't have any negative x values, so I'm going to draw mostly quadrant 1 and then like a little bit of quadrant 4. That should be enough. So mostly quadrant 1, a little quadrant 4. Here's my x-axis, here's my y-axis. So we're going to go up to 5. So 1, 2, 3, 4, 5. And I need to go to -2, no problem. We got it. And then in the x direction, 5. 1, 2, 3, 4, 5. Okay, so those are the vertices of the triangle. So we've got over here 0, 5, 2, -2, and then 5, 1. Okay, and they want the area of this triangle. Now they didn't give me equations of functions, but I could find equations of these 3 line segments very easily. I just have to decide, do I want to set it up in terms of x or in terms of y? I mean, you could do either. Is there always one graph on the top and one graph on the bottom? No, because notice here, right, the function on the bottom switches. So then you might think, oh, should I switch it so that I set my rectangles up in the y direction? It's no better because now notice you'd have to split it again. So it's really up to you. And since these are all line segments and it's easier to write equations of lines in terms of x, right, because of how we know slope, then I would say let's just leave things as they are, set up functions of x. So I'm going to call this line segment f of x. I'll call this one g of x, and this one down here h of x, okay? And we are going to have to split it here at 2, -2, because the function at the bottom switches from g of x to h of x. So I have two separate areas that I'm going to find. This one, and then I'm going to add it to this one to get the area of the triangle. Ooh. Okay. Beautiful. So now let's find equations for f of x, g of x, h of x, and then we can get going. All right. So f of x, it's a line. So first let's find the slope. So it goes through 0, 5, and 5, 1. So I can do change in y over change in x. So this is going to give me negative 4 over 5. And then I actually have the y-intercept for f of x, right? That's b. So I can go straight to y equals negative 4/5 x plus 5. So f of x is negative 4/5 x plus 5. 1 done, 2 to go. G of x. So slope for g of x goes through 0, 5, and 2, negative 2. So it's going to be negative 2 minus 5 over 2 minus 0, which gives me negative 7 over 2. Again, y-intercept for g of x is 5. It goes through 0, 5. So I can just go straight to y equals negative 7/2 x plus 5, which means I can write g of x as negative 7/2 x. That x doesn't look nice. Okay, negative 7/2 x plus 5. 5. Okay. Last one, h of x. So slope for h of x goes through 5, 1, and 2, negative 2. So that's going to be 1 plus 2 over 5 minus 2. 3 over 3 is 1. I don't have h of x's y-intercept, so I have to use point slope form here. So we'll have y minus y1. Let me just use this point 2, negative 2. So I'll have y plus 2 equals 1 times x minus 2. So y equals x minus 4. So that means h of x is equal to x minus 4. All right, now let's set up our integral to represent the area. So the first one, the limits are going to be from 0 to 2 to find that green portion. So the area is going to equal the integral from 0 to 2. I'll have f of x minus g of x. Since f of x is on the top, g of x is on the bottom, dx. Plus, and then we're going to go from 2 to 5. F of x is still on the top, but now h of x is on the bottom. Okay, and I'm just going to substitute in all the function values that I have. So the area is equal to 0 to 2. F of x was negative 4/5 x plus 5 minus g of x. So I'm going to distribute the negative. It's going to be plus 7/2 x plus 5 now dx. Don't forget the dx, ever. Plus 2 to 5. Then I'm going to have negative 4/5 x plus 5 minus x plus 4 dx. Okay, and notice, I know it's exciting to start anti-differentiating, but you want to make your life as nice as possible before you do so, meaning, notice here, oh, you know what? This should be negative, right? Because g of x was negative 7/2 x plus 5. So when I distribute that negative, this is going to be minus, and then now these 5's cancel out, okay? And also I can combine like terms here. So get a common denominator, clean things up before you start anti-differentiating, because you don't want to have more terms in your integral than necessary, because then you're going to anti-differentiate, and then when you have to evaluate the expression at your limits of integration, you're going to have even more terms, even more work to do, which means higher probability you're going to make a mistake. So you want to clean things up as soon as possible to prevent that from happening. So anyways, test yourself right now, pause the video, see if you get 27 over 2, okay? And if not, take note of why. Learn where you tend to make mistakes and be sloppy, and be aware of that moving forward. That way you don't repeat it. Okay, so that concludes the lesson on area between curves.